Hello everyone. In this video, we will connect an analog to digital converter to our FPGA and use it to sample a sine wave coming from a function generator. Once those samples are collected, we will calculate the fast Fourier transform in real time. We will do this by using Vivado and Vitis together. What you are seeing right now is the end result. The integrated logic analyzer is running in Vivado, and the serial terminal is open in Vitis. When we upload code in Vitis, the program runs and causes the FPGA to collect 64 samples from the analog to digital converter. After the samples are collected, the FPGA calculates the fast Fourier transform of those samples in real time. Both the sampled voltage values and the FFT results are printed to the serial terminal in real time. We will also walk through the entire block diagram so you can understand exactly how each part of the system works. Alright, so to start, we must go over the design from the last video. This video will build off that design, so if you have not watched the previous video, it is highly recommended that you go do that first. In the last video, the input vector was pre-initialized in local memory and would then be sent into the FFT IP core. This animation shows exactly how the design from the last video does the fast Fourier transform in hardware. First, the input vector is pre-initialized in local memory. Next, the processor writes the input vector into the FIFO through the bidirectional bus. Then, the FIFO sends out the input vector through its one-way output bus into the FFT. Then, the FFT sends in the output vector through the one-way input bus of the FIFO. Then, the processor reads the stored output vector through the bidirectional bus and stores it in local memory. Then finally, the processor then reads the output from local memory and sends it to be displayed on the UART line. This here is the complete design that allows us to sample the input vector from the analog to digital converter and then do a fast Fourier transform on that sampled data. The great thing is that we can reuse everything from the last video and only a few blocks need to be added. Of the new blocks to be added, only 3 are required. The optional block is for an ILA debugger. The first block to add is a custom block allowing the processor to send a start pulse to the analog to digital converter controller. The processor cannot send a start pulse directly, so it must instead send an AXI4-Lite write command to an AXI4-Lite slave block. The slave will then process that write command and generate a start pulse on its output. The slave implemented in this example generates a 1 clock cycle long start pulse every time it receives a valid AXI4-Lite write command to the register specified by the start register address parameter, with bit 0 of the written data set to 1. The start register address value is configurable, allowing the start register address to be changed as needed. To make this IP block, we must write a custom module in Verilog and then package it as a reusable Vivado IP block. To understand how the slave must be designed, we must first understand what happens when the processor executes an AXI4-Lite write command. In an AXI4-Lite write command, there are 3 phases. In phase 1, the processor tells the slave which register it wants to write to. In phase 2, the processor sends the data that it wants to write into that register. In phase 3, the slave sends a response back to the processor to confirm that the write command has completed. The specific details are summarized below. This waveform shows the behavior of our custom AXI4-Lite slave Verilog module when the processor sends a write command. The write first provides the target register address, then sends the data value that should be written, and finally receives a response from the slave confirming that the write completed successfully. In this example, the processor writes 0x00000001 to address 80000000, which causes the custom AXI4-Lite Slave Verilog module to generate a 1 clock cycle start pulse. The specific details of each phase are summarized below. For the sake of time, the Verilog that is used to make this custom block will not be derived. The code is instead provided in the project files and follows the behavior previously discussed. The second block to add is a custom analog to digital converter controller. This block receives the start pulse from the previous block and then uses the dout, chip select, and declock lines to sample 64 values from the analog to digital converter. After it is finished sampling, it sends out all 64 values using an AXI-Stream bus to a FIFO. To understand how the analog to digital converter block connects to the rest of the system, it is important to understand the purpose of AXI4-Stream. AXI4-Stream is the bus that lets our custom analog to digital converter controller send the sampled values into the FIFO. Once the values are stored in the FIFO, the software can easily read them later and use them for the fast Fourier transform. A brief explanation of how AXI4-Stream works is shown below. For the sake of time, we will not derive the Verilog for the analog to digital controller block from scratch in this video. The analog to digital converter controller logic and the AXI4-Stream logic each have their own dedicated videos. The last thing to explain is how the new blocks work together. Once you understand this flow, you will understand the main purpose of the added hardware and be ready to see the full design running in real time. To start, the processor sends a write command to the AXI4-Lite Slave block. The AXI4-Lite Slave converts that write command into a 1-cycle start pulse, which is then sent to the MCP3201 analog to digital converter controller. The analog to digital converter controller then communicates with the analog to digital converter, samples the input signal, and sends the sampled values out using AXI4-Stream. Those streamed values are stored in the AXI-Stream FIFO, making them accessible to the rest of the fast Fourier transform system. This here is the block diagram from the last video. Everything is exactly the same as before, meaning that if you followed along last video, you can reuse your progress. So to add the new blocks, we must go to the IP catalog. But what you will see is that if we search for our custom pieces of IP, there is nothing. This is because we must package custom pieces of Verilog to make them accessible by the IDE. Before we start, make sure you have a dedicated folder for this project. Within that folder, there should be 3 folders. One for the exported hardware, one for the IP blocks that we will package, and one for the workspace that Vitis will use. In the IP folder, there will need to be a folder for each piece of Verilog that we want to turn into an IP block. I already have the Verilog files added. If you purchased the book, then you will have access to the same project files and can follow along in the exact same way that is shown in this video. After setting up the files, we must go to Tools, then click the option to package IP. We want to package at a specified directory. We must then select the folder that contains the Verilog file we want to package. We can only package one Verilog file at a time, so we click the first one and package it. Before packaging, it's always good to inspect that there's nothing wrong with it. In this project, both Verilog files are written such that Vivado should be able to automatically get it right. Then, after inspecting, we package the IP. We must repeat the entire process again to package the second Verilog file as IP. Now when we search for our custom IP blocks, they will show and we can now include them in the design. We can also add in the new FIFO block. We can then begin connecting the blocks together. The entire process will be shown for you to follow along. Everything has been connected, so now let's do a quick check of connections. Now let's set the register of the slave IP block and add in the ILA. The final thing to do is ensure that all IP blocks have addresses defined. To do that, we go into the address editor. The FIFO that we added is not assigned yet, so it can automatically be assigned. There's still one missing address. That missing address is from the slave block that we added. To fix it, we must connect the bus line to the AXI interconnect. Then we can go in and automatically assign it. Vivado will know to automatically assign it to the address that we specified earlier. We now have all of the addresses defined, so we can now generate the bit stream. Now we go and export the hardware. When we export the hardware, we select the folder that we made for it at the start. For me, it was the folder named EH. After we have exported the hardware, we can launch the Vitis IDE and create a new application project. When creating a new application project, we must select the exported hardware file. Then we can give the project a name. We use the defaults on the next page, and on the last page, we click the Hello World template and click Finish. We then navigate to our source file and replace the Hello World code with our own code. The code for this project is provided in the project files that you get after purchasing the book. After you have copied and pasted the code, click the hammer at the top to build the design. After the design has been built, we can now wire up our FPGA with the function generator and analog to digital converter chip. The instructions for wiring the chip are explained in the book chapter dedicated to it. Note that the two capacitors are 10 microfarad and 0.1 microfarad ones, and they are placed across the ground and reference voltage pins. To ensure that our FFT is functioning correctly, we can set the function generator to frequencies that should trigger specific bins. The formula below shows how to calculate the frequency needed to excite a chosen FFT bin based on the FFT size and the ADC sampling period. The table below shows a list of tests that we can run to verify if the system is working. In Vitis, we must start by adding in the serial terminal. To do this, go to Window, click Show View, then search for the serial terminal. After you have added in the terminal, you can move it to the main box. Then to connect the FPGA to the terminal, click the green plus sign and select the right settings. In our design, the baud rate was 9600 and all the other settings were left as default. Then in Vivado, program the device to set up the ILA to trigger on the start pulse that gets generated. Then in Vitis, make a new run configuration. Then click on System Project Debug. Then click Target Setup and uncheck Program FPGA. Apply the changes and then run the program. Then in the serial terminal, you should see the FPGA taking samples and then printing the result of the FFT of those samples in real time. The 64 samples that were obtained from the ADC are printed first, and you can see that the ILA recorded the same values that were transmitted through the serial terminal with UART. This is great confirmation that the analog to digital converter chip is working correctly. The FFT result also looked right since it had a spike only at bin 1 in 63. Now let's do our second test. We should see only bin 2 and 62 spike. As you can see, it worked perfectly. Now let's do our final test. We should see only bin 3 and 61 spike. As you can see, it worked perfectly. Alright, so we have now finished explaining the entirety of how the fast Fourier transform works in FPGAs. In part 1, we explained the mathematical algorithm. In part 2, we explained how to make a custom FFT core. In part 3 and part 4, we ran a FFT using system-on-chip techniques. By watching all of those videos, you should be armed with everything you need to know to implement a fast Fourier transform in any digital system. Also, as a reminder, this playlist is based on a university course that I teach at the University of Texas at San Antonio. If you enjoy the content and are serious about mastering digital design, I highly recommend getting the book. The book includes the full library of experiments and project files, so it gives you everything you need to know to follow along and build the designs yourself. It also supports the channel and helps make future lessons possible. Alright, that's all for this video. If you liked the video or found it useful, be sure to like, comment, and subscribe. Looking forward to seeing you next time.